The presentation that I perform today is related to the effect of accelerogram selection for nonlinear dynamic analysis on the response of a liquefiable embankment. So this work was made in a collaboration with some colleagues from Centrale Supélec, Paris-Saclay, and from IRSN. So the presentation will be in the same line of the presentation of Professor Biondi and the Professor Arisi right before. So we try to move that. So what is the problem for us? In our case, the idea is that we need a large signal database in order to estimate the potential embankment failure, for example, in this case, sampling due to the nonlinear behavior of the soil. So in this idea, as I saw before, we can use real signal, real ground motions, or use it, for example, spectral matched synthetic ground motions. So when we put that, we have 3 questions, at least. The first one is the global nonlinear response of the embankment affected due to the fact that I use one or the other kind of signal?
Excuse me, Fernando.
Maybe the modified accelerograms, it means the spectral matched signal could replace the unscaled earthquake records. And the third question may be if the obtained levels of performance are similar for both types of motion. So we'll try to answer this question in this presentation. So this work is in the base of a performance-based earthquake engineering methodology. So it means, as Professor Biondi showed before, in this case, we try to study the liquefaction vulnerability analysis. For that, we need to identify the engineering demanded parameters and intensity measure to explain or to relate the behavior of the signals. Yeah. So in this case, here we have all the methodology proposed, but we focus in this presentation only in the part related with the hazard analysis and the structural analysis. The other work was made in order to complete this methodology using the same case study. So for this case related to the intensity measure, several parameters can be used as the acceleration amplitude, the intensity areas, the equivalent predominant period, the duration of stroke motion, etc., etc. And on the other hand, for the engineering demand parameter, as shown before, we can use the settlement of the crest of the embankment. It's the same, again, the same case as the Professor Biondi presentation. But other demand parameter can be used as horizontal displacement, per water pressure, etc., etc. So in our case, we study the response of embankment. Here we can see the geometry of the studied case. It's an embankment of 9 meters, placed in a foundation, liquefiable soil foundation, composed primarily principally by the loose medium sand and dense sand. Here, I don't know if you see my mouse. You can see the simulated response for the behavior of these 2 types of soil, for the dense and the loose medium sand. Look at the blue and the red curve, represent the modulus reduction as a function of shear strain. And also we have here the simulated response of the liquefaction test for both kind of soils. So here for the dense soil and here for the loose sand. So here we have the cycle stress ratio as a function of number of cycles. So the computation were performed in a finite element method using the code JEFDIN, that is a homegrown code at Central Supélec. In order to take into account the nonlinear behavior, we use the ECP elastic multi-mechanism model, known also as UJU model. So here I show you some criteria that are taken into account in this model. I don't bother you with the details of all the equation, but the most important thing is that the model is right in terms of effective stress. They use the column type failure criterion, critical state concept, and we have a Roscoe dilatance law. So more details can be found in the publication of our team. So now, if we move to a simple case, for example, here, we can see the one of the computations. So in this case, we have here in the top right, we have one signal, an earthquake accelerogram. We have acceleration in a function of time. Here we can see in the bottom the evolution of pore water pressure and the RU ratio. It means the variation of pore water pressure as a function of the effective initial confinement. As you can see that when it is blue, it is close to zero. It means that no liquefaction exists. And when it is red, you can see that it's a fully liquefaction. Okay, so here we can see the evolution in time of the liquefaction. We can see that we have the liquefaction in the free field place and in the middle of the embankment in this layer that is principally the loose sand. In addition, we can see in the top left the evolution of the settlement as a function of time. As you can see, compared here, that we have an increase of the settlement close to 4 seconds, then we stabilize, and a second increase of the settlement close to the 10 seconds. It is related, as you see here, to the accelerogram, the two black dotted lines is related to the 5 and 95% of the time duration. So it is clear that we have a induced liquefaction that produce a settlement in this case. So this is again one typical case. But the idea now is to go to study the performance of this model. So for that, I will show you two parts in my presentation. The first part is the input ground motion that we choose to study this problem, and the second part concerning the response of the embankment. So, as is the subject of the workshop, related to the input ground motion that we will use in a signal that will be placed at the bottom of the model and propagated into the soil to reach the embankment. We use two kinds of signal. The first one is the real ground motion that we use two data set. One data set related, named RM. We have close to 300 signals from many places in the world, many characteristics, but always recorded in an outcropping. And the second data set, we name it RL, is related to magnitude and distance, magnitude of 7 and a distance of 40 kilometers, that is close for a classical hazard analysis for any region. In this case, we are close to 19 signals. And on the other hand, in order to answer the question related to the synthetic ground motion, we use, as in the previous presentation, a spectral match in two cases. This is related to the work of the PhD thesis of Leven Isbiloglu from the ERSN. And in this case, as again, I don't go to the details of this part because we can show the presentation previously. We have classically a scenario and a spectrum for the hazard analysis related to the magnitude, distance, fold, so on. And we have in two cases, one strong motion database, that is the case for here, the real signal. We have the processing, the filtering and the other things. And in the other hand, we have some case, the ground motion prediction equation that proposes a spectral target spectrum in a site. We have several equations in this case. And the idea here is to perform a spectral matching in order to transform this strong, this real signal compatible with the spectral that we use in the region. Okay, so again, this is previously in the previous presentation. You have the method and the different points that you need to take into account in order to have a compatible spectrum. Okay, so again, it is not the focus of this presentation. So now we see the two spectral response of the two database. We have in the left side the spectral acceleration as a function of the period for the database RM. So here you have in green, you have all the used signal. On purple, you have the mean spectrum, the obtained mean spectrum, and in the dashed blue, you have the mean, more or less, standard deviation. And in the right side, you have the same representation, but in this case for the database named RL. Okay, so it is two kind of signal. Now, concerning the spectral match, we try to study two different cases. The first case, using the RM database, is to match all the signal to the mean of the database or to the median spectral of the database. It means we take this database and we modify all the signal in order to obtain the purple curve here. Okay, and it's the same if we take the median one. Okay, this is one of the cases to study. So here you can see the representation of all the data used, again in a spectral response as a function of period. And in the other hand, we can use the other database. This is a more classical case. It means that we have some signal and we have some ground motion equation or spectral target proposed in the ground motion equation. Here, for example, in the right side, we have the case of the ground motion equation proposed by Berger-Thierry et al. So here you can see the compatibility of the scaled signal with this spectral. And in the right side, you have the same idea, but using the ground motion equation proposed by Akar et al. So we can see that using the technique proposed by the PhD thesis, we are able to match this signal. Okay. So now the question is, what happened with the response of the world model? So in this case, we study, as again in the previous presentation, the crest settlement of the embankment obtained when we use all the database. So first of all, we use the real ground motion, its main unscaled signal. And here we have in the left side, the response obtained using the database RM. Here we have the relative settlement, as again, presented by the Professor Biondi, is normalized by the height of the foundation. So you have the crest settlement as a function of the maximum acceleration obtained at the outcropping. So here we can see that the settlement increase when the acceleration, input acceleration increase as expected by all. In addition, here we can place some damage level, that is the one proposed by the Swerwood, again as previously presented. So we can see that we have a large response of the dam. We have a lot of data that placed in a minor damage, moderate damage, a few placed in a serious damage. So now in the right side, you have the same response, but in this case, with the database named RL. So you have less data, but the behavior is similar to the previous one. So it means that it is a classical response using a real ground motions as input in the model. Now, if we compare with the response obtained using the synthetic signal, so we can see that in the, again, in the left side, you can see in green, the response using the real ground motion, and in the purple and in the blue dot, you can see the obtained values using the signal modified with in order to target the median spectral, and in the blue one in order to target the mean spectral here. So we can see that the response are inside of the green one. So in this case, we can see, okay, this is a classical response also. We will compare next. And in the right side, we have the same thing, but using all the modified signal with the green motion, the empirical ground motion spectrum, sorry. So here again, we can see that all the tested signal are placed in the minor damage level, and yeah, they are superposed to the one obtained with a real signal. A few signals don't work very well, but this is the next step in order to understand what happened. So now, we keep it with the real ground motions compared with the signal modified, again, with the median and the mean spectra. So here at the right side, we have the box plot showing all the response obtained using the real signal, the settlement at the crest obtained using the real signal, it means unscaled signal, and all the signal obtained with the median and the mean value. So here we can see that it is close, but I will make a zoom for you. And in this case, we normalize it by the mean value in this case, and for the median value obtained in this box plot. So it is more easy to see for you that if we use the signal using the spectral matching with the median spectrum, it seems that the mean value of this response is the same that obtained using the world signal. However, in the case of the mean value, it seems that I can obtain a higher value of settlement. It's not very big, but we have a difference. But the most important thing here is that Usually, if I move again here, you see that we don't have a lot of dispersion in the obtained spectral response, but sorry, the spectral of the signal, the input signal, but here related to the settlement, we have a huge dispersion. So we have the response using the same spectral signal, but not the same time history signal. We have a dispersion moving to more or less 5 or 15% of the expected response. So we increase the dispersion of the obtained signal. So maybe this is a thing that it is important to take into account for the use of this kind of a synthetic signal. Now, if we move to the case of the ARL database, so here again we have the response in a settlement is a function of acceleration, but here we compare with the 7th ground motion target spectrum that we use, and we can see here again a huge dispersion in both cases, and on the other hand we can see that we don't obtain the same distribution of the same response, and it is depend of the spectral that we use to match our signals. Okay, so this is very interesting. But now the question is, it is clear that the signal that we use in a synthetic case are not real signals, because in a real signal, all the parameters of our EM are intercorrelated each other. But what happens if we compare, for example, in this case, the median value of a matched data set with a real signal, here in this case, the green one, that we consider is the closest unscaled signal to this spectral. It means that we compare a real signal with an unreal one, and we divided here in this case for each case, particular case, and we can see that in most of the case we overestimate the response of the embankment, the system, related to the response obtained using a real signal. And in two cases, but it is maybe perspective in this world, we have, for example, for this 2-1 case, we have an underestimation. So this is one of the problems that we can found here, and the question is why. So I think if we move to the seismic hazard, here, for example, we can compare the statistical of a few intensity measures. I don't know if you see clearly. We can make a zoom here, maybe. And here we have the two databases. The database, the real signal is again unscaled signal, compared with the one using the scaled one. And in the orange, we can see the relation between 3 EM parameters. For example, here PGA, PGB, and the effective duration. We can see that we have a large range of values. It is normal because it's the whole database. But when we modify the signal in order to match the one on spectral, it is clear that we reduce the dispersion in terms of PGA on PGB. But here, the most important thing is that we don't reduce the dispersion in the duration, the effective duration of the signal. So it means that this is not very well related with the other parameters. So it means that this signal, this synthetic signal, is not a real one, and maybe this is the fact that this is the reason, sorry, that the response of the embankment of the model using this kind of signal is not in agreement with the one obtained using a real signal. So it's the same for the other database. So we have always the same problem. The fact that modify the signal introduce some bias in the obtained parameters that describe the earthquake signal. So to finish, I think that I respect the time. Some key points from this work. So in this case, the soil liquefaction induced settlement for an embankment due to real and synthetic motion were studied. We used a performance-based earthquake engineering methodology to show the response of our model. And in this case, we use synthetic motion that were obtained using the spectral matched method. 3 points important concerning the intensity measure. The synthetic motion are compatible with several target response spectra. So we are able to find this kind of signal. In the contrary, concerning the engineering demand parameter, the dispersion of the relative crest settlement increase when the synthetic motion are used. And another fact is that the intensity measure of a real earthquake signal are interrelated, which is not the case for the synthetic motion. So thank you for your attention, and it is all for me.